So how can we leverage these mathematical properties of our stabilizers and build circuits that can actually detect errors and correct errors? So here on the diagram to the left, we see an encoder. So the encoder is the part of our circuit which will take our raw qubit and encode it into this larger state space. And then after the state has been encoded, we presumably have some error channel that is inducing noise, and then we leverage a syndrome extraction circuit, which uses our stabilizers to then detect the errors that the error channel imparted on our system. And I want to try to give a little bit of intuition for how this works. So, at a high level, the total state that's comprised of our logical qubits and this auxiliary qubit shown in the bottom part of the circuit with the subscript A, is the ket 0 with subscript A. This composite system I'm representing with psi here on the right hand side. So what happens, the Hadamard gates in the circuit create a superposition and split the state space across a few different components. One of the branches here has the logical state that's correlated with a measurement outcome of 0 on the auxiliary qubit here. And there's another branch of the superposition that has an association of where the auxiliary qubit will always be measured with the state of 1 when an error occurs. And so in this case, when we see that this auxiliary qubit is measured with value 1, we know that an error occurred and we need to apply the correction. So another important point here is that this syndrome extraction is a type of parity check that does not collapse the state. So we can do this check multiple times and our encoded state remains in superposition. Whatever the state it is not disturbed by our stabilizers. So a little bit more detail here. It's okay if you don't follow this, but it is interesting. This is the state that this simple stabilizer circuit is creating. In the two branches of the superposition, in branch 1, we have the sum of identity operations plus our stabilizer operations, which are Z gates in this case, operating on our logical state. And so what happens when there's no error, when this E operator is actually identity, so no error, what happens is that in branch 2, what we have is the difference between identity minus stabilizers acting on our logical state psi sub L, and E is identity, as we said. So this collapses to 0. So when no error occurs, this branch that has the auxiliary qubit with measurement value 1, that would be measured as 1, it collapses. So this is excluded from the set of possibilities. And so what we will measure is this value of 0 at the auxiliary qubit, as we mentioned. Now, conversely, if there is an error, and let's say we're expecting X errors, then what happens is in branch 2, because of we've designed our stabilizers to anti-commute with the errors, Z does anti-commute with X, and so if you were to propagate this X error to the left through, there would be a sign change resulting in a positive sign in branch 2. So we would have constructive interference in branch 2, and which essentially leaves the auxiliary qubit that it would be measured with the value of 1. And in this case, branch 1 then vanishes due to this destructive interference. So these stabilizer circuits, what they do is they allow us to leverage the mathematical properties of our stabilizers and interference to detect errors using simple measurements that do not collapse our logical state.